So the thermohaline circulation is also part of the overall cycling of carbon and carbon dioxide across within the Earth system. I don't want to go into this in any detail. It's not terribly relevant to what we're going to do here. Just want to point out that we think about water, we think about air, we think about movement of ocean currents and atmospheric patterns. They are very important in where CO2 gets moved in the Earth system and how that cycle operates in the Earth system as well. Especially as CO2 is most soluble in cold water, it's absorbed at high latitudes, and it's outgassed in tropical regions. So again, CO2, we can store it in cold water, but obviously the warmer the water, the more it comes out. So if we see the oceans as a store of carbon dioxide, as a possible store of, let's get rid of some of this excess CO2, as the water gets warmer, its capacity of the oceans to hold CO2 gets less and more is outgassed. So again, that's the sort of side effect, if you like, of the Earth system. So, effectively the ocean currents, therefore, are more complicated than the atmospheric systems, but they are bound by the same basic principles, but they operate in water masses and according to circulations that are more complicated than in the atmosphere, especially these gyres, these circulatory water flows, and that although the thermohaline circulation may be the sort of underlying key concept, actually it's a little bit more complicated than that, and our knowledge of the ocean system is still not that good that we can't begin to understand exactly how it's likely to operate in the future. So if you're looking at predictions into the future, you would expect ocean projections to be more uncertain than atmospheric projections. So the IPCC could give you quite reasonable models of atmospheric projections, simplified down, probably work quite well. Modelling the ocean is much more difficult. And the oceans, of course, being 71% of the surface, are very important heat stores. And this is why, for instance, things like the pause, the global pause in climate change, one of the accepted explanations for the pause is that actually it's the oceans that are warming, especially at depth. But we can't monitor this to the same as we can monitor what's going on in the atmosphere. So it's always going to be a less certain part of the Earth system, of the atmosphere circulation system. Basic reading, oh dear, 2 eyes, choline. Oh well, never mind. I'll see that. Now there are 2 sites which I would recommend which actually look at ocean circulation over time. These are 2 nature education sites which are really sort of syntheses of ocean and atmospheric circulation and abrupt climate change. I'm not going to go through these, I'm going to go through this paper with you, but I would recommend that you do have a look at those and get a feel for how these patterns actually have changed over time and how we've tried to understand these changes over time. I would give a health warning that because the THC is under threat as a concept, if the THC as an overlying concept were to be questioned and to be found wanting, then a lot of our knowledge about future changes in the ocean system would change. And therefore it is quite likely that we might, over the next 10 to 20 years, have quite a radical rethink over just how the oceans actually work. It also has the advantage that we're mapping, we're monitoring the ocean, so we can actually say more about how they operate. Right, what I'd like to do, and I think rather than have another break, is to actually go through this the Agulhas paper, because what it does, I think, is show how to read a paper. I'll show you the bits not to read, but also to try and get you to understand the sort of moving down from the global to a slightly more regional way, the way currents actually operate. And it does have some very nice pictures in it, which help. So, not going to try and find it any other way than on my stick. Right, so there's one.
So, do we have first viewing on it? Do we have first viewing on it? Is that the house?
Right, if you can sort of see. I'm using this paper as an example paper because I haven't given you huge amounts of reading on this because this first part of the module is very much sort of, in a sense, factually based about understanding the basic processes. So you'll be aware that up until, if you looked at the exam paper, then up until, I think modelling, up until and after modelling is section 1 of the exam, which is short answer questions on the topics that we've dealt with. It's trying to show a basic understanding of the basic processes. So I haven't sort of given you loads and loads of papers to go in great in-depth understanding of these systems. The second part, where we try and look at how we've gone into the past to understand the systems, are we're examining by essay base, and there will be more reading and more paper reading. So I haven't given you a load of papers to read. The ones I've done is to try and get you to sort of understand the basics. Now, the importance of this is that this is a sort of idea that's just come in over recent years. So this was 2011, and it relates to this fundamental thing of the idea that the northern hemisphere steals heat from the southern hemisphere. The idea that this ability of the northern hemisphere through the ocean system can steal the southern hemisphere heat. And that in fact what drives climate in the northern hemisphere and climate change is a function of how much we can get from the southern hemisphere, or whether the southern hemisphere says, Yahoo sucks, you're not having our heat, I'll keep it ourselves, and the northern hemisphere loses an important part. And this is the first decent study of this Agulhas system that goes around southern Africa. So let's have a little bit of geography to begin with. Okay. So, first of all, what we're interested in is the link between what happens here and what leaks into the AMOC. So effectively, the AMOC, remember, is not just driven by heat and water from the equator, it's actually stealing this water from the southern hemisphere. And the question is, how much and what sort of water can and have we stolen? So we have, here's the AMOC, here's the Brazil current, which is a western current. So the western current is moving away from the equator, taking heat, but it goes into this little gyre, or rather large gyre across here, and then we can see that there's water moving up towards the equator here as the leakage. So it's then the question about where does the water, this water, come from? Is it just water that is being heated up in the gyre, because that's what happens in the southern Atlantic, or is it actually stealing much hotter water, warmer water, which generates from through here? Notice down here, here's Antarctica, nothing at all happens around here. Well, it does, but it's effectively not complicated at all. It just goes round and round and round. So your poor duck around the Antarctic will just freeze it, what's it off, and it just goes round and round and round, and never gets out of the Antarctic. You feel very sorry for it as it bleated its way around there. So, the crucial area is what happens around this bit here. And there's two ways in which you can look at this, and two ways in which the you could try and understand this. One is to actually observe water moving, measuring water moving. What temperature is it? What salinity is it? What density is it? Where has it gone from? Where does it travel? That is very difficult because it's a very large area and it's very expensive to monitor. So we do rely on modelling, and models can be constructed which model the basic physical properties of these water masses and suggest that water does generate from here and does drive and help drive this leakage which eventually gets into the North Atlantic. But if you look, what you see is that here there are certain patterns that we can see. And what this paper does is to look at the nature of how that actually happens. And I'll use the diagrams, I think, to show rather than try and go through it. So a situation which is known as these Agulhas rings or leakages. This is how water leaks from the Indian Ocean into the Atlantic. And it's this thing called the Agulhas retroflexion. Effectively, around these big gyres are eddies, are sort of small, like mini gyres that go off. And the idea is that when you get around these margins here, these little eddies form, a bit like smoke rings. You imagine sort of a big ocean person with a big mouth, sort of having water in it go like a smoke ring, pushing it out into the Atlantic. And you see this retrofaction whereby water comes this way and is then affected by water moving in this direction, and also by this cold water to the south, is forced into these little eddies. And the idea is to what extent this water can effectively be expelled as these little rings or leakage into this system. Once the water gets into this system, it can either get trapped into here or it can actually go up through there. So the diagrams, I think, probably show the whole idea best. I'll use the diagram here. Right. So what the observations are trying to do is to say, well, how much water does come through here and what actually happens. So normally what happens, you've got a very warm Indian Ocean. Remember, the Indian Ocean is really quite trapped. It's really bounded. It's difficult to get water out of the Indian Ocean. It's a big gyre. It's close to the equator. It's very hot. So you can see that